Hello and welcome to this online CPD looking at steel floor construction. My name is Richard Dixon and I'll be taking you through the topic today. We'll start the presentation with an introduction covering a bit of history for steel floor construction and how it's evolved over time. Then we'll have a look at different forms of construction currently used in the market. Following that, we'll move on to an overview of the design performance of steel floors. Everything that we'll cover in this section is considered in greater depth in other CPDs. So if you're interested in more detail on any of the topics in this section, you can watch the appropriate CPDs to learn more. And finally, we'll have a look at other aspects of what we've termed efficient design. As engineers, we often consider efficiency on the basis of steel intensity, that's kilograms per metre squared or kilograms per metre of the beams used. But actually that's only one part of the picture, and we'll look at the impact that fabrication and erection can have on overall costs, which may inform how we develop designs in future. In the days of old, which in this context means that BC is before composite, precast was king, with precast units placed on top of the structural steelwork to form the floor. The beams were designed non-compositely, and if you wanted to reduce the overall depth of the floor construction, then you'd use shelf angles within the web of the beam. Then the radical breakthrough eureka moment came when composite construction arrived in the 1980s. Instead of craning in individual precast units, bundles of profile metal deck are lifted into place in a single operation and rapidly laid out to form a safe working platform. Composite action is achieved by through-deck welding of shear studs to the beam. Edge trims are added to retain the concrete during the casting operation, the mesh is set in place, and then the floor slab is cast. Composite construction resulted in a 50% weight saving on the steelwork and a 30% reduction in floor depth compared to non-composite construction. Along with the health and safety implications of forming the safe working platform quickly and the much faster speed of construction, it's no surprise that the introduction of composite construction changed the market forever in multi-storey buildings. Composite construction also enabled lighter, shallower, short-span solutions, introduced elegant, spacious, clear span solutions, and other combinations of construction too. The top photograph begins to introduce the whole aspect of service integration that we'll explore in more detail later too. Shallow flooring systems were also developed, starting with slim floor, where a UC section had a plate welded to the bottom flange and shear studs fixed to the top flange. The fabricated beam was then cast within the floor slab, resulting in a shallow floor construction. Once the market had been proven, British Steel developed a deep deck system, now called Comflor 225, to span longer distances without propping, and rolled asymmetric sections or ASBs with an emboss to the top flange to generate composite action. The ASB eliminates the fabrication processes to add the plate to the universal column and the shear studs to the top flange. The deep decking and ASBs form the slim deck system that you may be familiar with, and that's been in the market for 20 years now. Here we see the impact of composite construction had in the market. Following its introduction in the 1980s, it radically changed the market, with steel moving from a market share of 33% in 1980 to the high 60s, low 70s market share that it's enjoyed for the last decade or so, with that market share gained predominantly from concrete. One question that's often asked is, how much does structural steelwork cost? To answer this question, Gardner and Theobald published some indicative cost ranges based on actual contract values in a quarterly article in Building. For multi-storey construction, select the appropriate frame from one of the three options. Add the floor system you're considering, and fire protection, and it'll put you in the right ballpark. If you're considering a single-storey building, simply select the appropriate portal frame option. Costs are of course location dependent, so the values from the cost table should be adjusted in accordance with the appropriate BCIS index for the location where your building will be constructed. The variation is significant across the country. If you took the City of London rates, which have an index of 116, and applied them to a project in Belfast, you would actually be overstating the price by almost twice what it would actually cost to construct that building in Belfast, where the index is only 61. All of the tables on screen were published on the 27th of July, but are updated with each article. Please use the link shown on the screen to get the current versions of the cost and location factors. Of course, if you're after something more project specific, the best thing to do is to contact a steelwork contractor. Moving on to look at an overview of the construction types. Steel floor systems can be broadly grouped into three forms of construction. On the left we have traditional downstand composite, where a standard beam section has the shear stud welded to the top flange to form composite action with the slab. Simple off-the-shelf stock items are used in this system. For the clear span cellular, it's formed by taking either a standard universal beam section and then splitting it, or by fabricating the section from plate. Cellular beams started off life as castellated beams with hexagonal openings, but have become standardised on circular cells to avoid stress concentration around the openings. Because of the fabrication process, you have the option to have lighter top T and a heavier bottom T where the steel is working harder. We then have the shallow floor system that has the ASB integral with the floor slab. Looking at each in a little more detail, we can see that the downstand composite is very simple. It's straightforward both as a design concept and as a fabrication process. This is the fabricator's favourite because sections run steadily through the shop, subject only to standard processes, making it very efficient for them. It's mainstream. It's the default system used in the market. Availability isn't an issue as it uses standard sections. There's an established infrastructure both from a fabrication perspective and for deck availability and installation, so it's a very competitive solution. For clear span cellular, this too is mainstream, though the size of the market is smaller. This is because we need to balance the benefits of clear span and weight savings, because the steel's where we need it for structural efficiency, against the additional fabrication costs of forming the beams. As a rule of thumb, cellular will come into its own when looking at city centre developments of greater than 5 stories. Obviously, where smaller buildings require long span solutions, it will also be appropriate. With this system too, there's also the opportunity to minimise the depth of floor zone by passing the surfaces through the openings in the beams, and we'll see the benefit of that shortly. The final one of the three systems is the shallow floor system. It's not so mainstream due to the fact that it's structurally less efficient than the other systems and therefore heavier. However, it does have the benefit of being shallow as it incorporates the beam within the slab. Its use is therefore often driven by limitations on floor zone depth for a building rather than structural efficiency. Summarising the different options then. Downstand composite is the lightest form of construction, low cost and structurally efficient, as can be seen from the stress diagram and the depth to the centroid of the tensile stress block. Cellular construction is the lightest form of construction, but comes with additional fabrication to form the section. But the structural efficiency is demonstrated by the increased depth to the centroid of the tensile stress block when compared to the downstand composite system. For shallow floor, structural efficiency is restricted by geometry, resulting in smaller depth to the centroid of the tensile stress block, which results in a heavier section and therefore a more expensive system than downstand composite. Why would you ever contemplate using shallow floor construction then? Well, that's because there are other aspects of the project, such as external envelope, that contribute more significantly to the cost of the building than the frame and floor cost alone. Looking at a typical building, external envelope has been calculated at 24% of overall cost compared to only 9% for frame and floors. So using a shallow floor system may reduce the height of the building, resulting in less area of cladding, offsetting the additional cost of frame and floors with a reduction in the external envelope. Alternatively, there have been instances where for the same building height, the developer has been able to include an additional floor, increasing the lettable area at little additional cost. Big picture factors may be more significant than relative differences on an elemental basis. Looking now at floor zone depth, when we consider a 200mm raised access floor, a 500mm service zone and 150mm for suspended ceiling construction, it should come as no surprise that the shallow floor system performs well with a total floor zone of 1180mm. When we consider an equivalent downstand composite, we see that the floor zone increases to 1340mm. However, perhaps most surprising is the impact on cellular construction if you can integrate the services. Clear span secondary beams can achieve a floor zone depth of only 10mm more than the shallow floor system. But if we can't integrate the services, we see that figure rises from 1190mm to 1690. Having reviewed the different types of systems, we'll now give you some thoughts on how to select the system that will best suit the project you're considering. On the basis of span, the reckoner on screen might be helpful, though there's nothing hard and fast about the ranges quoted. We can use short span composite floors with universal columns and shallow solutions typically up to 7 metres. Short to medium spans would tend to favour standard composite downstand construction. And for clear span solutions, either downstand or cellular should be considered. But when we get to greater than 15 metres, then cellular comes into its own and will be the system of choice. Another choice to make is whether to adopt a cast slab on profile metal decking or to use precast concrete units to form the floor. Both have even shares of the market and together comprise over 80% of floors constructed in the UK. Some key points to note here are that during construction, there needs to be careful consideration of installation schedule of the precast units to avoid introducing torsion into the steelwork. This isn't an issue for metal decking as both sides of the beam are cast simultaneously, giving a balanced load to the beam. There's also guidance on the effective width of the slab that can be considered as part of the composite beam. With metal deck, you would use secondary steelwork to suit the span of the deck profile, whereas precast can span between grids, although primary beams would tend to be deeper. Also, often overlooked is the requirement from a detailing perspective to use a minimum flange width of 180 mm in order to land the precast units and allow for construction tolerances. This will result in a minimum of a 406 by 178 UKB section. For metal deck, a minimum flange width of 100 mm is required. Considering some of the practical aspects of both types of construction, the main differentiator is speed of construction. As we saw earlier, bundles of floor deck can be lifted into place in a single lift, whereas each precast unit must be lifted individually. Using precast, you may be able to avoid any casting operation on site, but that's project specific and in fairness, you tend to use in conjunction with the screed anyway. In final construction, you tend to have a shallower, lighter floor with a metal deck compared with precast. It's simpler to deal with penetrations through the floor, as precast manufacture is all about throughput of standard slipform units, so it's better to deal with openings on site. In terms of features, you have a ribbed soffit with metal deck, which can be pre-painted, and a flat soffit for precast. Although if you were going for an exposed soffit, it would probably be better to go for an in-situ solution rather than precast for a better finish. However, the way that the surfaces are dealt with can negate any preferences on finish. For example, surface-mounted conduits for wiring result in an industrial feel to the finished exposed soffit, which suits either a ribbed or flat soffit for the floor. For reference, here are some typical metal deck profiles and their typical spans. For Comfloor 51 you have the benefit of a predominantly flat soffit, but at a cost since the dovetail arrangement isn't the most structurally efficient. And for Comfloor 60 and 80 you can see that the profile has been detailed in such a way as to allow optimal position of the shear stud in the centre of the trough, rather than having to be offset. This means that the shear capacity of the stud is consistent and not affected by the direction that the shear force is applied. And for design and detailing of both systems, P300 and P351 are the design guides that you need. However, manufacturer's software will usually comply with the requirements of the guides on ponding, level, pre-camber, etc. Although some details required for precast can be very helpful if you wish to use the units compositely. A more recent option for composite floor construction is the Fibreflor system. It combines standard Comfloor metal decking with a combination of polypropylene and steel fibres to eliminate mesh reinforcement. Whilst not applicable on all projects, it can be cost effective and save up to 20% on the programme by eliminating the handling and placing of mesh. The different types of fibres fulfil different roles as are listed on screen. The system has been tested and can achieve up to 120 minutes fire resistance. It's designed using the Comdeck software from Tata Steel. One concern with systems incorporating steel fibres has been whether fibres will protrude from the slab after casting. As can be seen on the picture, though they will be visible as the concrete is placed, the first float moves them from the surface of the slab, resulting in a standard finish. To sum up then, you have a lot of choice, but often we're not comparing like for like. If you recall the span table that we saw, shallow floor and clear span cellular are both effective solutions, but you wouldn't use them for the same building. Use of the building after construction may also influence which system should be adopted. For offices, clear span construction is the obvious choice, whereas the depth of construction and regular grids due to standardised layouts often lead to shallow floor solutions for residential. Clear span or short span? Well, the break-even point is typically 5 stories in the city centre building. Anything over that and clear span should be the preferred option. Downstand composite is the most economic solution and is therefore a good starting point. However, the most economic frame solution is only one aspect of the wider project considerations that the design team must consider, so it should be viewed in the context of the bigger picture. And finally, there's a choice between metal deck or precast concrete slab, and now the option of Fibreflor. Having reviewed the different types of system, we'll briefly review steel's cost competitiveness. This comparative cost study was developed by an independent team from Gardner and Theobald, Peter Brett Associates and Mace, and originally published in Building on the 20th of April 2012. The cost information is updated quarterly to keep the study current. It considers 2 buildings, Building 1, a low-rise business park office, and Building 2, a high-rise city centre office. We'll look at each in turn briefly here, but there's a lot more background information on the steelconstruction.info website, where you can find the original published article too. For Building 1, it's a 3-storey building of 3,200 metres squared gross internal floor area, and a floor plate width of 18 metres to give an open plan space. The clear floor to ceiling height is 2.8 metres. It also includes a 150mm ceiling and lighting zone and a 150mm raised floor. It's a typical brick-clad business park office. From a structural perspective, the grid is 7.5 metres by 9 metres, with columns supported on mass concrete pad foundations. Appropriate standard practice service zones were adopted for the different frame options, and a 30-minute fire rating was provided. The options considered were steel composite beams and composite slab, steel frame and precast concrete slabs, reinforced concrete flat slab, and an in-situ concrete frame with post-tension slab. Core construction was braced frame for the steelwork options and concrete shear walls for the concrete options. Reviewing the outputs of the study, we can see that for the frame and floor costs alone, the standard steel composite construction is the cheapest at £140 per square metre, and flat slab concrete is the most expensive at £155 per metre squared. Steel with precast and post-tension concrete flat slab are comparable. However, when we assess the implications on the foundations from the superstructure, we see that the lighter weight of steel superstructure results in a saving on foundations, and in fact both steel options are cheaper than the concrete ones. Both of the steel options are also faster to construct, resulting in significant cost savings for the steel options compared to the concrete ones when considered for the building as a whole. The lowest steel option is the steel composite on metal decking at £1,535 per square metre, whereas the cheapest concrete option is £1,610 per square metre. All of the numbers in the table are City of London rates, and we need to apply our location index if considering a building elsewhere in the UK. The figures quoted were updated for the 27th of July 2012 article in Building. Please reference the latest information via the link at the bottom of the screen. Moving on to consider Building 2. This is an 8-storey speculative city centre office building of 16,500 metres squared gross internal area. It's L-shaped with a double height reception area. The clear floor to ceiling height is 3 metres. It also includes a 150mm ceiling and lighting zone, but the raised floor is 200mm. It's clad with a standard curtain wall system. From a structural perspective, the grid is 7.5 metres by 15 metres, with a CFA piled foundation adopted for both options. Appropriate standard practice service zones were adopted for the different frame options, resulting in different floor-to-floor heights. The steel option integrated the services through the cellular beam. A standard 60-minute fire rating was provided. An alternative foundation scenario using steel bearing piles as an alternative to CFA piles was also carried out, the details of which can be found on the website. There were only two viable options to be considered for this building. For steel, it was a cellular composite beam solution with a composite slab. For concrete, it was a post-tension band beam and slab with in-situ columns. Core construction was again braced frame for the steelwork option and a concrete shear wall for the concrete option. Any basement construction would be common for both options and therefore was excluded from the study. Reviewing the outputs of the study, we can see that for the frame and floor costs alone, the steel option is the cheapest at £194 per square metre compared to £210 per square metre for the concrete option. Again, we can see that the lighter steel superstructure results in lower foundation costs and that the steel option is faster to construct, resulting in a significant cost savings for the steel option compared to the concrete one of £61 per metre squared on the whole building basis. This cost differential is also supported by the market share figures that we saw earlier. If there wasn't a significant cost differential between the options, then steel wouldn't enjoy the high market share in a cost-driven market like construction. Again, all of the numbers in the table are City of London rates, and we need to apply our location index if we're considering a building elsewhere in the UK. As before, the figures quoted were updated for the 27th of July 2012 article in Building. Please reference the latest information via the link at the bottom of the screen. Okay, we now move on to an overview of the design performance of steel floors. As I mentioned earlier, everything that we'll cover in this section is considered in greater depth in other online CPDs. So if you're interested in more detail on any of the topics in this section, you can watch the appropriate CPDs for more information. Firstly, looking at sustainability. Here we see some of steel's sustainability credentials. Its high strength to weight ratio means that we don't use very much of it in a steel frame building. Even a rudimentary assessment of embodied carbon should look beyond a simple tonnes of CO2 per tonne of material and should at least consider the intensity in terms of kilograms per metre squared for different systems to allow the intensity of different materials to be considered. It also enables clear span construction, effectively giving a blank canvas to fit out the building, enabling it to be reconfigured as necessary to meet the needs of new tenants and ensuring that the building doesn't become prematurely redundant. It also results in a lighter superstructure, minimising the resource impact not only of the structure itself but also of the foundations. It's interesting to note that if you were viewing this presentation 10 years ago, before sustainability was recognised as an important issue, these characteristics would all be present, as they're also characteristics of simple steel construction. A key point to recognise then is that good, efficient design in steel is actually good, sustainable design too. Multicyclability, low embodied carbon and thermal mass will be covered in the next few slides. This table shows the recovery and recycling rates of constructional steelwork. There's a well-established global scrap industry, and scrap steel has a value, and because of this, it's always been recycled. The recycle rates are very high, and very little, if any, material finds its way into the waste stream at all. In 2004, a disused building in Teesside that had been erected in 1956 was demolished, and the reclaimed 20,000 tonnes of steel was tracked to identify where the steel ended up. It was used in over 30 different applications, including the Kingsferry Bridge to the Isle of Sheppey, the Paddington Station redevelopment, Heathrow Terminal 5, the West Stand at the Oval, light steel framing on a residential development in Cardiff, in Ford Transit vans and other motor vehicles, and finally on 2p pieces for the Royal Mint. And of course, at the end of life for each of these applications, the steel will go back into the melting pot and be used again in new applications for yet another cycle. With steel, that process can go on ad infinitum without any loss of mechanical properties, so a coin can become a bridge and vice versa. Steel is not just a recyclable material, it's a multicyclable material. A question we're sometimes asked is, what's the embodied carbon content of structural steel? Well, the value varies dependent upon the specific product and how it's manufactured. But as a rule of thumb for structural sections, this value is about 0.76 tonnes per tonne. Adding fabrication and erection elements, this results in a figure of around 1 tonne per tonne of as erected material. However, remember that we need to consider intensity of material, so any comparison should be done on a kilograms per metre squared basis rather than a tonne of CO2 per tonne of material. As part of the cost comparison project, Peter Brett Associates also undertook an embodied carbon assessment for the options considered for Building 2, the 8-storey office building. Using an ordinary Portland cement mix for the concrete in both steel and concrete options, we can see that steel had a 19% lower embodied carbon content than the concrete option. Using a replacement mix is sometimes considered to reduce the impact of the concrete. We can see that though the difference between the steel and concrete options narrows, the steel option still has a 10% lower impact than the concrete option. And replacing the conventional CFA piles with steel bearing piles also has a positive impact on the original study arrangement. Buildings are commonly designed with passive cooling strategies nowadays too. This is to take advantage of the thermal mass of the structure. This is a valid approach, but there is a misconception that we come across on occasion that using thermal mass would lead toward one type of frame material rather than another. In a building, the mass utilised is that of the floor slab. Admittance is the correct measure of the concrete's ability in the floor slab to absorb and then discharge heat over a duodenal cycle. It can be seen from the chart resulting from research at City University and from Oxford Brookes that anything over 100 mm can't be utilised for thermal mass, and there's greater than 100 mm of concrete in all floor systems in a steel frame building, as there is in a concrete frame building. Interestingly, adding extra mass by increasing the depth of the slab will have a slightly negative impact in terms of performance, but also negative impacts in terms of resource efficiency, increasing the weight of the structure, requiring larger foundations, but have no benefit at all in terms of performance. Moving on to consider fire protection. The common fire protection systems are boarded systems, intumescent coatings, where under fire conditions the coating chars to provide insulation to the steel to achieve the design fire period, and less commonly in the UK, cementitious sprays. As can be seen in terms of market share, the green cementitious sprays have declined over the last 10 years, such that now they're only seen on projects with strong American influence. Intumescent and board systems dominate now, with the ratio broadly reflecting the ratio of columns, where we would use boards, to beams, where we would use intumescent. Applying the intumescent coating off-site is also an option, and this comprises typically 27% of the total market. We don't typically need to protect all of the structural elements. P288 gives guidance on the established practice of protecting only primary beams and columns in the UK. In terms of floor vibration, we see here the link between theory and practice. P354 gives a procedure for design of floors for vibration, and the table demonstrates performance in practice. The key aspect to note from the table is the column on the right, where we're looking at R, the response factor. For hospitals, a response factor of less than 1 is required, so we can see that we're well below the requirements in terms of performance in this onerous sector. And briefly looking at acoustics. Similarly, we have P372, which gives guidance, and P371, which is a series of case studies that demonstrate performance. With careful attention to detail and supervision of workmanship on site, steel buildings can perform well in excess of the regulations in terms of acoustics. The figures shown are ballpark, but give a good indication of how each element of the floor makeup contributes to the rating of the floor, providing that good flanking details are constructed. They are confirmed by case study measurements taken on a composite floor construction in Grantham. Okay, moving on to our final section, we'll look at the different aspects making up efficient design. Traditionally, as engineers, we would measure the efficiency of our design by considering steel intensity. However, when you look at the build-up of costs of erected steelwork, you can see that whilst raw materials are significant, there are other aspects that are just as significant. Fabrication contributes 30 to 40%, and erection on site contributes 10 to 15%. Similarly, fire protection is at similar levels. and we'll look first at the fabrication aspect through a worked example. We'll use a simple example for a 1500 tonne steel frame with off-site intumescent to illustrate the impact of fabrication costs. We've got some rates here, but please don't think that they are in any way representative of the market today. These numbers reflect the height of the market in 2007, but are consistent across all aspects. For example, the £800 per tonne for raw materials would be in the order of £550 per tonne now. So for illustrative purposes, working our way through the pie chart, we can see the following. That our 1500 tonnes of raw material contributes a cost of £1.2 million or 41% of the overall cost. Our 1500 tonnes requires fabrication at say £500 per tonne and contributes a further £750,000 to the total build cost. Our 12-week construction programme contributes £420,000 and 20,000 metres squared of fire protection at say £22 per metre squared contributes a further £440,000. We need to transport our material to site and that contributes £45,000, and engineering hours for design and detailing at £30 per hour contributes a further £90,000, giving us a total of just under £3 million or £1,963 per tonne. However, by increasing the amount of steelwork from 1500 to 1550 tonnes, although it has a negative impact in terms of raw material, enables simplification of connection details so that stiffeners and welding of these stiffeners is no longer required. The fabrication rate has therefore reduced from £500 per tonne to £400 per tonne, reducing the fabrication cost from £750,000 to £620,000. The erection programme remains unchanged, contributing £420,000, but through increasing the weight of sections, we can adopt a single coat intumescent system rather than the multiple coat system originally required. Our application rate has therefore reduced, giving the contribution of £300,000 rather than £440,000. We're transporting an additional 50 tonnes, so the transportation costs have increased slightly, and we've had to do some additional design work to simplify the fabrication, so that's increased from 3,000 hours to 3,200 hours. However, when we add up all of our costs, an additional 50 tonnes of steel has resulted in our total cost reducing from just under £3 million to just over £2.7 million, and our rate per tonne reducing from £1963 to £17.56. Why is that? Well, most fabrication shops are set up for throughput, where standard sections undergo standard processes as they pass through the shop. Whilst complexity sometimes can't be avoided due to project geometry, it's more economic to avoid details with lots of stiffeners in favour of slightly heavier sections. As we've just seen, the effect of fabrication costs is far more significant than that of nominal additional material. So unless complexity is driven by external factors, it should be avoided wherever possible. A couple of useful rules of thumb can help you assess the impact of different connection details. It takes around 20 minutes to lay a 1 metre length of 6mm single run fillet weld, and 20 hours of fabrication time is equivalent to 1 tonne of steel in cost terms. Okay, that's all very interesting, but how do you use it? Here's an example that a steelwork contractor received of a heavily stiffened 14 metre long column using a 305 by 118 universal column section. Total material cost was 1652 kilograms for the section itself, plus 160 kilogram for base plate and stiffeners, and 115 kilogram for connection stiffeners, resulting in a total material weight of 1,927 kilograms. There's a total of 55 metres of 6mm fillet weld, and using our rate of 20 minutes per metre, dividing 55 metres by 3 gives us 18.3 fabrication hours. With a 1 tonne of material the same price as 20 hours of fabrication, the equivalent cost of material for the welding is 18.3 divided by 20 equals 915 kilograms of steel. Therefore, the total equivalent cost is 2,842 kilograms. Compare that to using the heavier 137 or 158 kilogram per metre sections, where the connection and base plate stiffeners aren't required, and you can see a significant cost saving by reducing and eliminating extensive fabrication. So just to summarise this section, Taking the standard simple fin plate connection as our base point, you can see the impact of an end plate connection. However, we're not really comparing like for like, as a fin plate connection will be for simply supported beams and an end plate for moment connections. Perhaps the best comparison is the stiffened end plate rather than the standard end plate, where connection stiffeners are required to transfer the moment. On the basis of earlier discussion, it would be worthwhile assessing whether increasing the section size of the beam will result in only the standard end plate connection being required and possible cost savings on the overall costs. Sometimes fabrication complexity can be hidden by the way in which we view the connections. Looking at the stick representation, there's no obvious issue at all. It all looks pretty straightforward when we put the beam widths in. But when you start to think about the connections, you can see that we have to notch the flanges of the beams, add end plates, and deal with the clash of bolts fixing the beams to the columns, which can only be overcome by welding plates across the toes of the column for a standard end plate connection for the beams that were originally connected to the column web. From an engineer's perspective, we need to avoid preferential details. That is adding stiffeners or specifying minimum weld size, because that's how I've always done it, or that's what worked on our last job. For example, if the fabricator's design indicates that a 6mm fillet weld is required, don't insist on a standard 10mm weld. The impact isn't simply the ratio of the 10mm weld to the 6mm weld originally specified. It's actually 3 times, because you need 3 passes to lay down the same required weld volume for a 10mm weld compared to a 6mm. So a 10mm weld requires 3 more passes than a single 6mm weld, so will take 3 times as long. Okay, we'll now have a look at the final piece of the jigsaw, the impact that erection can have. As you recall, whilst not as significant as material and fabrication costs, it's still worthy of consideration. Whilst fabrication decisions on connection details will obviously impact how a structure is erected, another less obvious factor that engineers can consider is the impact of piece count. Here we see 2 options for the same floor area. Using the traditional engineer's measure of steel intensity, we can see that it's a very simple decision to make. We go for the 20 kg per metre squared short span beam option rather than the 32 kg per metre squared clear span secondary option every time. However, we can see that with the short span layout we have 9 beams and 6 columns making 15 pieces in total, compared with 5 beams and 4 columns making 9 pieces for the clear span secondary option. So what difference does that make in practice on site? Well, erection of our 9-piece clear span secondary layout completes this area of floor. As each piece occupies the same amount of crane time, for the same time we can erect this area using the short span solution. To get the same area with the short span, we need to erect the other 6 members. But during the same time, for our clear span option, we could have erected this area. And so we go on. Similarly, we can see that although clear span primary has a steelwork intensity slightly lower than that of the clear span secondary, the reduced piece count should lead to the selection of clear span secondary layout unless other factors dictate. Okay, to sum up then. We've seen the differences of different types of floor construction and reviewed when and where they're typically used and the comparative costs of steel v concrete frames. We've also looked at the performance of steel frame buildings, reviewing the guidance that's available and showing that the theory is backed up by proven performance. And given some food for thought by looking at the big picture of costs and shown that focusing only on the steelwork intensity may not always result in the lowest cost structure. To quote someone who's got a similar sense of humour to my dad, and apologies for that, shedding pounds in a weight sense doesn't always result in less pounds in a cost sense. There's also cost information available from Gardner and Theobald on the cost of structural steel construction for multi-storey and single-storey construction, and cost comparison information of steel versus concrete for low-rise and multi-storey construction. The cost information is updated quarterly through Building Magazine and on Steel Construction Info too. And that concludes the presentation on steel floor construction. Thank you very much.